Hi, in this video we start the implementation of the ternary search tree. So let's get started. I'm going to create a package called ternary search tree, and we are going to have a node class. It's going to represent the characters in our tree. And of course, we are going to have a ternary search tree. I'm going to denote it as TST. And of course, a class from which we are going to test our data structure. Okay, so let me start with the node. So class node with object. Okay, we are going to create a init constructor, and we are going to have a character equals to character. We will have a character, and as we have talked earlier, we have a left child equals to none in the beginning. We will have a middle child. Let me call it node. It's not child, it's nodes. Middle node is equal to none, and we have a right node is equal to none in the beginning. So all ternary search trees has three children: a left node, a middle node, and a right node. And a trie, for example, an airway trie, has as many nodes, as many children as the number of characters in the alphabet. So for example, in the English alphabet there are 26 characters. I'm not sure, but I think there are 26 characters. So the trie has 26 children, but there is lots of null pointers, and that's why it's not so memory efficient. And that's because I'm a great fan of ternary search trees, because it's much more memory efficient and we can do a lot of stuff with the help of this data structure. So it's definitely overperform the trie data structure. Okay, so I'm going to talk about that's all about the node. Okay, the TST is going to be the tree data structure itself. Okay, it's going to have a constructor in it, and we will have a root node, just like the binary search trees. Root node is equal to none in the beginning, and of course it's like a hash map. We have put and get methods. So that's why usually ternary search trees becoming very popular as far as data bases are concerned, for example, because we can avoid hashing. Hashing in practice is not so efficient as in theory, because we cannot create a perfect hash function. And with the help of ternary search trees, it's much more efficient. We don't have any hash function, so it's not going to it is definitely outperform hash tables and binary search trees, as well as we have talked in the theoretical video. So here I'm just going to define the put and the get methods. It's going to have self. We will have a key and a value pair. Okay, self dot root node is equal to self dot put item. I'm going to put item. Okay, we will have a self dot root node. We will have a key. We will have a value, and we will have an index from 0. Okay, so I'm going to define the put item method. It's going to have a self. It's going to have a node, a key, a value, and an index. And first of all, we have a character. We get the characters from the key by the index. And if the root, I mean another root, the node is equal to none, that means that we instantiate it. with the character, and else if the, I mean not else, but another if is the c is less than the node dot character. We just have to know that left child equals to, we go to the left, self put item, we call this method recursively, with node that left child, with the key, with the value, and with the index. We are not increment the index, because as in we have talked about it in the theoretical video. We just keep incrementing the index if it's a match, but it's not a match because the c is less than the node that character, which means that in the alphabet it precedes the given character. For example, c precedes d, whatever. If the c, the character is greater than the node that character, which means that it is proceed. It is a successor. Here is the predecessor, it is a successor. So the node, that right child, right node. I think that we have a right node. Okay, right. Yeah, I'm not sure why this offered me the right child, because there is no right child at all. Anyways, the right node is equal to self that put item on the node that right node. Okay, I get used to the child, but it's not the best name. Okay, if the index is less than the length of the key minus 1, it means that it has to be the middle node. We know that if it's not less than, if it's not greater, it means that it is equal to, but we have to check whether the index is less than the length of the key. And if it's smaller, then we have to put it in the middle node. So self that put item with the node that middle node with key with value, and we have to increment the index here. Okay, index plus 1, and else we just have to it means that the index is not less than, but it's not less and not greater, and the index is not less than the length of the key minus 1. We just have to set the node that value is equal to the value. So we just insert it, and we just have to return the node. Okay, we have to import, so from ternary search tree that node import node. Okay, so I'm going to define a get method with self and the key, and I'm going to have a node is equal to, we just have to check whether the if node is equal to none, then we just have to return a none, and else maybe it's going to be the get. Oh, here we are not going to check it. We just have to node equals to self that get item, self that root node, self that root node with key and 0. If the node is equal to none, we just have to return none, and else return the node that value. So we have to define the get item method. It's going to have a node, a key, and an index. I'm going to implement this method, and we are going to test it in the next video. I don't want to make this video very long. So thanks for watching. In the next video we are going to implement this method and test our data structure. Thanks for watching.